So let's start the next session. Are you all back from the coffee? Yeah. So let's start the next session, which will be presented by Andrea Boratin from the Technical University of Denmark, and it will be about process mining in a streaming setting, discovery and conformance. Let's make an applause to Andrea and.
Hi everyone, welcome. So, I was very lucky that Chiara presented just before me because she introduced a lot of things that probably I can run quite quickly on. In particular, this idea of post-mortem data, right? So the idea of post-mortem data, as Chiara mentioned, is that you analyze the data from a historical point of view. And my claim is that this is in general very good. So all the techniques that you have seen during the week are very good for forensic reasons, meaning you want to go back and you want to check how were the processes being executed 6 months back. Were there any deviations? Were there any bottlenecks? But the point, the main problem is that these results are somehow outdated by design. And what I mean by that is that the results are not really directly useful for improving the processes that are currently being deployed. So you cannot really use information from 6 months back to hope and improve the current process. Of course, as Chiara presented, you can use them for learning purposes under the assumption that history sort of repeats itself, right? And that's a bit the point on why we need streaming process mining. For example, imagine that you have a web application being deployed, which is, for example, to report taxes, yeah? Or imagine, for example, an e-commerce website. You want to know if the users of this website are getting stuck into some, deadlock or in some functionalities. You want to know this information immediately so you can provide some feedback, some suggestions to those users so they can, complete their goal. If you think about an e-commerce website, you don't want to have the users of this e-commerce website to be unable to complete the order, because then the company does not get any money, right? So that's an example of a use case where the bottleneck identification is extremely important to happen in real time, immediately. So you can immediately do something about that. Or if you think about the healthcare domain, right? I guess there are many people working with healthcare in here, and you know that there are these clinical protocols in place, right? So essentially what in this school we call processes, referring on about how to treat patients, yeah? And of course, you want to know if a patient is being treated according to the protocol before the treatment is over and maybe the patient is dead. So you want to know if something is not being aligned with the protocol immediately so you can drift the execution and the treatment of the patient back to a proper treatment. And these are just a couple of use cases where it makes, where if you think about that, post-mortem process mining makes very little sense except for forensic reasons. And so the goal of streaming process mining is to tackle these kind of scenarios. But when we talk about streaming process mining, we have two main entities, two main elements that we need to cope with. The first is the stream itself. So the stream is typically assumed to be an infinite sequence of events. And these events are essentially emitted immediately after they are executed. And there was a question before about how can we communicate these events? Like, how can we write on the log? And let me anticipate the answer to I think you asked this question, right? And there are many systems, many messaging systems designed specifically for these purposes. MQTT, Kafka. There are many protocols that can help with that, right? But the point is that we have this infinite stream. There is this infinite stream. No, that's too challenging. There is this infinite stream of events. And of course, all process instances are intertwined between each other, right? So if we want to separate, to isolate different cases, of course, we need to do that afterwards. And that's essentially the first distinction that you probably can intuitively identify. Meaning when we do post-mortem analysis, you can always group your process instances based on the case ID, right? So queries like, how many events are in these process instances? What are the starting events for process instances? These kind of questions are fairly easy to answer. But in a streaming setting, because the events are just generated, the events are produced when the event is actually executed in reality, you completely lose this capability of grouping your events per case, because the only let's say, element, the main element here is the time, and is the fact that all your events are sorted by time. Yeah? So that's about the stream. But then we have a second element that we need to keep into account, which is the observation window. Meaning that in a streaming setting, the idea is that you see data just when you are explicitly trying to look for it. Right? So you switch on somehow your miner, you keep it on for a while, and only during that period you can do your mining. And this is what is called the observation window. So now if we take the stream and the observation window into account, we have some complexities, some issues that are starting to emerge. Specifically, so here you can think of this of the x-axis as somehow the time dimension, right? So the easiest situation is when we have the our trace, which starts and ends within the boundaries of your observation window. But that's of course a very lucky setting, because it could easily happen that we see just the beginning of our trace, but not the end. Or we can have the dual situation where we see the completion but not the beginning. And of course we have the very unlucky setting where we just see a subsequence of our execution. And this is actually the most general case, right, which is the main focus of streaming process mining. And you should not think of these as a very exceptional case, especially when you're dealing with very long process instances that in the healthcare domain, it's not so uncommon to have process instances lasting for weeks or months. Then you start to realize that this case is actually not so uncommon as you would expect. Yeah. So when we talk about so streaming data mining is something that has been around for quite a few years now. And just to give you a brief overview of the differences between analyzing streams and analyzing data, let me put this comparison about the capabilities about what you can do on a database and on a stream. So essentially, when we talk about a database management system, like for example the systems that you have been discussing about the previous days, so an event log, you can think of it as a database where you have some properties. The point here is that the relations, the properties are somehow persisted in this database, which means that you can randomly access different parts of your data, and therefore you can perform one-time queries. For example, you can have one query that will tell you all the events that are the first events of all process instances, right? What are the first events appearing in all process instances? You can extract this information with just one query. In a streaming setting, because the stream itself is just about these events that are just being communicated, you have these transient observations, which means that the access to your data is sequential. So you see one element at the time and you don't know what's going to come afterwards. And that calls for a completely different, querying mechanism, meaning that you cannot do a query like, give me all the events that started my process instances, but you need to continuously query the stream, meaning you need to set up a query which keeps listening for on the stream, and this query keeps listening for all the initial activities on all process instances that will come. Yeah? So it's a completely different sort of paradigm. And from a computer science point of view, these requirements come with a bunch of other properties that are very peculiar and very funny to work with for a computer scientist. Meaning the fact that you need to do just one pass on your data because that's your stream, and because the stream is assumed to be infinite, you cannot store it, which means that you need to have approximations in place. This also calls for the impossibility of doing unbounded backtracking, meaning you cannot go back as much as you want in your processing. And some other properties, like because the stream is infinite, we need to assume that our data or the underlying model will change sometime in the future, which means that we need to accept the fact that there will be a concept drift sooner or later. As well as other time constraints. So for those familiar with the term big data, I guess that's all of you, you know that big data has been characterized with, I think initially 3 V's, now I don't know how many V's are there, and if you know why just the letter V, just approach me later in the coffee break and tell me. But if you look at most of the properties of big data, you will see that the streaming kind of approach there's a good overlap between dealing with big data and the constraints that are imposed by the streaming computational paradigm. Yeah? So there are some techniques to do process mining on stream, so to do streaming process mining. And in the rest of the presentation, I will use this sort of taxonomy. So I would like to divide the possible approaches to handle streaming process mining into 3 main categories. The first is window-based models, meaning models where we essentially collect events for a while, and then we apply offline techniques. Another family of approaches is called problem reduction, meaning we take a simple problem in the stream data mining domain, and we try to rephrase our more complex streaming process mining problem in terms of this simpler problem. And finally, offline computation, meaning trying to squeeze as much of the computation complexity offline, so before we actually switch on our observation window. And of course, that's not, an exhaustive taxonomy, so we need to assume that there are mixes of all these approaches. Yeah? So in the rest of the presentation, I will go through examples of these 3 approaches. But before I start, is there any question on the setting, on the scene of the problem, or is everything clear? Yes? Couple of questions.
Thanks. I'm not sure if it's a little bit too early for this question, but in terms of evaluation, we learned before about the data split for predictive monitoring, and I was wondering, because we had this validation that goes all the way through time, I was wondering how you can approach this in a stream, because as you have sequential, you cannot go infinity through time for the validation set, for example.
Correct.
And how does this split work?
So typically the evaluation is constructed by, simulating a finite stream for which for example, if we're talking about the discovery, what is the process that generated the data for each period of time. And then you compare the streaming discovery with the expected results. But of course, you need to do that for just a finite set of data, which is typically simulated. And then it's important also to mention that the metrics used for the validation are slightly different. Because, for example, you have the delay in the recognition of the concept drift detection. You have a bunch of different metrics for that as well.
Okay, thank you.
Other questions?
Okay. I have a question in the previous slide. So, stream process mining approaches. So, it means I just want to clarify my concept. Like in an interactive or in a real-time world, data is coming, and in the form of stream, which is generated from the process, and real-time data is being mined, or
that is correct. That is correct.
Real-time data at a specific period of time. So,
So the main constraint from the real-time point of view. So if you talk to real-time persons, they will start talking about deadlines and so on and so forth. The main point that we focus on is that each event, so your algorithms are expected to have constant computational complexity per event.
Of course.
Processed.
Of course.
Right? Meaning that you have a certain amount of time, which is constant complexity, to handle your event. Yeah?
So, real-time data is coming, events are happening, and real-time mining approaches are applied, and then results are getting.
Correct.
And my question is still the same. The events that are generated from the process are stored in which kind of way?
They're not stored.
So
That's the whole point.
how we will, if we need some information later, how we will get that event log of the process?
You don't. That's the whole point. The stream is infinite.
Okay.
You don't store information. It's like MQTT. So you keep listening for these happenings, and we will see in 1 second when you do the window-based model, you record a bit of events, but in general, you don't want to store those events. That's precisely the point of the streaming techniques.
So it doesn't mean there is a loss of data?
There is, and that was exactly my point here. Approximation needs to be in place.
Okay.
Good.
Thank you.
Thanks for the opportunity of clarifying. Yes. Keep in mind that I have 45 minutes. So, and I'm at slide 6 of 2000. So.
Very fast questions.
Yes.
Okay, the first one is how to distinguish between actual events that are related to a process and noise events.
Yeah.
This is my first question, and the second one for predictions and for predictive models. How to train the models during the real time or during the incoming of new events at each time window, let's say. Thank you.
So. For that, you should talk with Chiara for the second question, right? But but there are, as far as I know, there are algorithms that are capable of, doing the learning or the updating of the model in real time. So preserving those computational constraints that I've talked about. The first question I forgot. All right, we will see those in 1 second, hopefully. Yeah?
Hi. Would you not require pre-processing of the streaming data? And if you do, how would you work with that?
Yeah, so yes, there is some pre-processing that might be needed. We will see one pre-processing later on, but in general, the idea is that here we focus on events that are already cleaned up. And there are many techniques, for example, to handle events that are arriving at the order which is not the correct one, right? There are other techniques that can be leveraged to pre-process the data. But in here, we assume that the data that we have is the data that we want to actually mine. No? So yes, let's move on. So first part, window-based approaches. That's, I think, quite, I can go quite quickly here. The idea is that we collect event for a certain time period, and then we can construct basically an event log, and we can process this event log. Everything should be quite obvious here. There are many ways of constructing these event logs. So should we just keep the last n events that we have seen, or should we do other approaches? There are many ways of collecting these observations, these recent observations. Count-based window, time-based sliding window, tumbling window where there's no overlap, for example. But everything boils down to this idea of collecting events for a while and then applying a standard offline technique for process mining. Yeah? So the meta algorithm, if you will, is that we have this never-ending loop. Every time we observe a new event, we refresh our memory, so we put this element into our memory. Here, if we assume to have a count-based sliding window, we just basically need to check. So we insert our event into the memory, but if we don't have any memory available, meaning we filled up the memory that we had, we need to dequeue the first element that we have seen. So we need to kick out the oldest element. And then we can just convert our memory into a log, and then we can apply our standard offline process mining technique, right? Conformance checking, discovery, whatever. Simple approach, any offline technique can be used, all good. It's terrible in terms of memory usage. That's really awful. And just to give you an example, think about doing the discovery. So you want to do process discovery in a streaming setting, and you have a memory available, for example, for 10 elements, but then you immediately see 20 traces starting at the same time. Then your memory will be immediately filled with just the first event of all those parallel instances running. So intuitively, I hope you see that that's a terrible way of handling the memory. Yeah? So let's move straight to the second family, which I call reduction-based approaches, and I will show you these techniques on the discovery problem. So the problem that we will use for presenting this technique is called the frequency counting problem, and it is essentially the frequency counting problem. It is essentially the problem of you have your stream and you want to count how often the variables that this stream is made of are being observed. Yeah? And for example, when you look at the Twitter trends, yeah, that's one instance of the frequency counting, meaning that they're basically counting each and every hashtag or topic, whatever you want to call it, and they want to keep this counter fresh. So the time dimension is important. So they want to see what are the topics or the hashtags that are the most used over the shortest amount of time, recent amount of time. So it's not the absolute counting of those hashtags, but it's the counting in the recent history. Yeah? So you see immediately that it's super important to keep the forgetting. The forgetting is typically the key part in streaming settings. You don't want the absolute count, but you want to forget old information. Yeah? And one very well-known algorithm for tackling this problem is called lossy counting. Yeah? So let me give you a bit of an idea of this lossy counting. So we have our stream made of variables that here are represented as these gray boxes like A, B, and C. It is a lossy algorithm, meaning that there are mistakes in the counting, yeah? But you can specify the approximation error for your counting, epsilon. And the main data structure that this lossy counting uses is we call it D, and it's basically a set where each element of this set has three components. So the variable that we are actually counting, the frequency for the given variable and the maximum error in the frequency that we're making. Yeah? And then there are some other information derived from that, meaning the bucket size. We will see in a second what that is, which is derived from the epsilon, from the error, and the ID, the number of the current bucket, which comes from the number of observed item over the size, the size of the bucket. So we have our stream here, and these are the ID of the buckets. So right now we're in the bucket with value B current, and the next one will be B current plus 1. And every time we see a variable, we need to essentially check whether this variable is already in our memory or not. Yeah? Whether we have seen this variable before or not. So if we have seen this variable, then we can just simply update the frequency. We can just increment the frequency component for that variable. If we haven't seen this variable, then we need to add this variable to our data structure. So we need to add a tuple made of B, the variable that we're looking at. The frequency is 1, because it was not in the memory, so it's the first time that we see it. And the delta, so the maximum approximation error, should be set to the count of the current bucket minus 1. And in 1 second, we will see an example. And then the most important, I mean, not the most important, but a very important element is the cleanup, the housekeeping of the data structure, which is basically to remove all elements fulfilling this inequality. So the frequency plus the approximation errors should be less or equal to the current bucket. So let's see an example here. We have the first bucket, so B current is equal to 1. And after each box, the color indicates the variable. So by the end of the first bucket, we have these frequencies for each color, and the maximum approximation error for all of those is 0. Because remember that here it's B current minus 1. And because we're in the first bucket, the approximation error is 0. Yeah? Then we need to remove all elements fulfilling that inequality. So at the beginning of the second bucket, this is the new configuration, and we keep the counting. We keep counting our elements by reapplying this algorithm. Yeah? And I need to speed up a bit, but what's important is that by the end, these are the estimated frequencies on that example, and these are actually the true frequencies. Yeah? And there are a bunch with these approximation errors on the estimated frequencies, right? And there are a bunch of, this algorithm is quite nice because there are a bunch of properties that are proved for it. In particular, that the true frequency is bounded by the approximated and the approximated plus the error, right? And these frequencies is also bounded by these other elements. So it's a well-studied algorithm in the streaming mining community. And there are many versions of it. For example, there is a version of lossy counting with budget, so with a fixed memory as well. So there are many versions of this algorithm. But that's not for process mining, right? This is for frequency counting. But so let's now try to bring this algorithm into process mining. And how do we do that? Well, if you know the heuristics miner, I guess most of you heard at least about the heuristics miner. You know that two of the most important heuristics of the heuristics miner are the dependency measure and the end measure. And the key is that both these measures are actually defined in terms of these relations here. And these relations are basically saying how often activity A has been seen directly before activity B. Yeah? So the intuition here is that these are essentially the variables that we want to count. So how often two activities are happening one after the other. And once we do this, let's say, conceptual switch, then we can rephrase the whole problem as a frequency counting problem. Yeah? So to do that, we actually need two of these lossy counting data structure, one to keep the latest activity in the case, and another to keep the actual counting of these frequencies. And I will completely skip the algorithm because of time, but the point here is that it has a very good memory management, but of course it introduces some complexity as well, which is maybe not the best. But of course, you know, the problem is a bit more tricky, so we need to accept that. Yeah? So take-home message of this family of techniques is that the idea is that we take a problem that has been solved already for a simpler case, and we try to rephrase our problem in terms of this simpler solution. Yeah? And there are many other techniques, but all of them boils down to the idea of, you know, you have your events, you construct an intermediate data structure, and here, when in the updating of this intermediate data structure is where typically the problem reduction happens, based on the type of the intermediate data structure that you want to have. Yeah? Any question on this idea or on the sliding window? So on the window-based model or on the problem reduction approaches? No question. That's very good. I'm very glad to hear that. Good. Yes. What? Time is short indeed. So offline precomputation. You recall that in the beginning we have discussed about the sliding window reduction and offline precomputation. And here the idea of these techniques is to handle with the time complexity or the time constraints that are imposed by the streaming setting. And I will show these techniques while talking about conformance checking. So you will see both discovery and conformance checking. So when you consider this process model, that's a simple model where you have just a loop in the beginning and two branches in mutual exclusion at the end. If you calculate the offline conformance with respect to this model for these trays, you get a conformance 1, so we're good. But if we take some other executions, like for example the second one, you see that the second one will give you a conformance value 0.8, even though the behavior that you see in these trays is actually perfectly fine. The only problem is that the trace stops at the event at the activity B, right? The third example is also quite fine, but just from activity B onward. And the fourth example is a subtrace, which is actually fine, but it is missing the head and it's missing the tail, right? So I hope that you're now connecting what we discussed at the very beginning, meaning that here meaning that perhaps having just one value to discuss the conformance in a streaming setting is not enough. And in particular, it is perhaps relevant to discuss the conformance. So how good is the behavior, whether the behavior that we have seen is aligned with the process or not. But also we want to discuss about the completeness. So have we seen this trace in its entirety, or have we seen just, you know, a couple of events? And what we called confidence, so how many events are still to come in these trays? And here we use the term confidence, meaning that how confident is the conformance value? So is there a lot of behavior still to come, and therefore can the conformance be completely messed up, or is the conformance quite stabilized? So when you think about these conformance measures or these dimensions, and when you look at the offline conformance of the traces that we discussed earlier, you see that actually all these traces, from a streaming point of view, they don't have any problem in terms of conformance. They all describe behavior which is allowed by the model. Yeah? The problem is that the last two traces have completeness problem, meaning that they were expecting something beforehand, And the second and the fourth are also expecting something afterwards, right? So because of the stream and the observation window, I think it's important to, in a streaming setting, to emphasize that conformance by itself is not enough. You need to pinpoint also whether there are missing information. And in the technique that I present here, I will go very quickly over it, but you find all the details in the chapter. So sorry for that, but time is running. The idea is that instead of computing the conformance, for example, using alignments, we compute the conformance of small patterns of behavior, and in particular, for example, direct following relations. And to do that, the idea is to construct a data structure which comprises 3 elements. So a set of direct following dependencies that are allowed by the model, and then 2 additional data structures that are somehow indicating where, in which position, this direct following dependency is supposed to happen in the trace. Meaning P, which stands for past, is telling us how many distinct patterns are we supposed to see before a given pattern, and F, which stands for future, tells us how many patterns are we going to expect afterwards. Yeah? So metrics that, elements that are directly mapping the 3 metrics that we were discussing before. So for example, if you take BC, we will have the past 2, 4, meaning before that, we're expecting any number of distinct patterns between 2 and 4. That's where the 2 is coming from, so those 2, and the 4 is coming from basically any repetition of the loop. And we can have as many loops as you want because we're just counting the distinct direct following relations. Yeah? And similar for the future. So I will skip the details of how to do that, but the idea is that we take our patronet, we construct the reverse patronet, meaning the patronet where each edge has opposite direction, and by applying some unfolding and constructing the reachability graph, you can very easily compute these data structures. Of course, doing these operations here, so the unfolding and the construction of the reachability graph, is extremely complex from a computational point of view, but that's not a problem because we do that beforehand. We do that offline. Yeah? So that's the main, and I will skip the algorithm as well, but the main idea is that these 3 steps, so going, for example, from a BPMN to the patronet in order to construct this intermediate data structure is very computational complex, but that's done offline. And then what we need to do online is actually, just checking the conformance between this data structure and our stream. And that requires just constant time complexity. And the trick here was to squeeze the computation beforehand. Yeah? Of course, when doing these kind of operations, a lot of approximations are introduced. And to answer the evaluation question in this context, one way of that we used to evaluate these was to check the correlation of the conformance between this technique and the offline alignments. And though you see correlations, of course, those are not super strong because of the approximation that we needed to introduce in the construction of this data structure. Yeah? Good. So, conclusions. Yes, thanks. I think we're on time. So, I skipped half of the slide, by the way, so that's why we are on time. But never mind. Conclusion. So, the take-home message. What I hope you take home from this session is what is streaming process mining? So streaming process mining is process mining on live data. Yeah? And process mining on live data means process mining where we have, where we need to accept having partial information and where we have very specific constraints, computational constraints. Yeah? Why stream mining is relevant? Why do we want to do that? Think about the healthcare domain, right? So that's relevant when you want to improve the processes that are currently running. So not forensic reasons to understand what happened last year or 10 years back. You want to improve the current processes, the current executions. That's why it's relevant. And how to perform? Well, I hope that I gave you a bit of a framework of the techniques. We have three main strategies, window-based models, problem reduction, so taking a problem already solved in the, in the stream mining community and try to rephrase our process mining in terms of streaming, the data streaming problem, or offline computation, meaning trying to squeeze as much of computation offline by doing some caching or processing of the elements before the actual observation window starts. That's it. Thanks for the attention and some questions.
Thanks a lot, Andrea. Questions? 3 minutes for 2 minutes for questions.
Sorry, I have a question about in the page 24. Yeah, please. Yeah. Always this. Yeah, so I just have the question about the second one traces. That means the second trace. Second trace for the completeness. Why we think about this is correct. That means this complete the traces.
So the completeness
refers
to the completeness from the beginning of the trace. So
Okay.
is answering the idea of the completeness is, has this trace, have we seen everything for this trace up to this point in time?
Okay.
Yeah?
Okay.
Because the assumption here is that what we see, so what we don't see in the future is because this has still to come.
Okay.
So the completeness refers to the past, essentially.
Okay. And also for the confidence,
Yes.
for example, for the comparison about the second one and the third one,
Yeah.
why is the third one is a high confidence and the second one is a low confidence, please?
Because the idea here, so the confidence is looking at the future, right? So I think, so that's how, so the completeness is with respect to the previous observation, the confidence is with respect to the future. And the idea here is that if you look at this trace here, it stopped at B,
Okay.
right? Which basically means that there are still some events to come, so we cannot be really that confident about this behavior.
Yes.
Because there's still behavior to come, so maybe this trace will be completely messed up by the end. Instead, for the third trace, this is a trace that already reached the end, so we do not expect anything else to happen, and therefore we can be quite confident about the conformance that we computed up to now.
Okay, thank you very much for
Yes.
the explanation. Thank you.
You're welcome.
Okay.
Get C, then confidence becomes high, right? Because then all the choices have been made.
It will not, it will become higher. Yeah, correct.
Okay, I think that we do not have time for other questions. Maybe Andrea is
Yes.
around, so you can ask him questions there.
Yes.
Let's make a big applause now.
Yes.
The final one. Thank you.